Reactions can be of two types. Either it can be irreversible or reversible. Irreversible reactions are unidirectional reactions that happen only in one direction. For example, when carbon reacts with oxygen, you will get carbon dioxide. This reaction is unidirectional reaction because you can't get carbon back from the carbon dioxide. It is an example of combustion reaction. When you burn something, you can't get it back. Now come to the reversible reaction. Reversible reactions are bidirectional reactions. For example, conversion of water to water vapor. This reaction is bidirectional because we can get back water from the water vapor. Let's take one example. Here I have taken water in a vessel and kept it in the sunlight. You will observe after some time water start evaporating and vapor goes in the atmosphere. So this reaction is unidirectional reaction because water vapor leaves the container. You can't get it back in the container. Now here I have placed water in a closed container. Here water vapor cannot leave the container, so they condense back in the form of liquid. In the closed container, this reaction will be reversible reaction because you can get liquid back from the water vapor. Now let's study this reversible reaction. Now we have to study reversible reaction. To study it, we are going to plot a graph in which we are going to plot rate of the reaction on y-axis and time on the x-axis. In this container, rate of evaporation will be high at the beginning, but it gradually slow down. After accumulation of some amount of water vapor, condensation will start. So at the beginning, rate of condensation will be very low, but gradually it increases. And at a certain point, rate of vaporization and rate of condensation become equal. And at this point, you can say equilibrium has achieved. So what do you understand by equilibrium? Equilibrium is a state in which opposite forces are balanced. Or you can say when forward and backward reactions occur by the same rate, then you can say system has attained equilibrium. Now again observe the same experiment. In the first case, when the vessel was open and vapors are allowed to go in the space, so there will be no revert reaction or the condensation reaction is possible. So in that case, equilibrium cannot be attained, or you can say equilibrium cannot be attained in an open system. While in the closed system, vaporization and condensation, both the reaction can take place. And at a certain point when they become equal, equilibrium can be attained. Or you can say equilibrium can be attained only in the closed system. Let's examine the same reaction. This time we are going to plot concentration on the y-axis and time on the x-axis. When evaporation just has started, the concentration of water vapor was very low, but gradually it started building up and it attained a constant value. In the beginning, concentration of water was high, but it decreases gradually and attain a constant value. At a certain point, concentration of water vapor and water, they both attain a constant value. This point is known as equilibrium. Now we can say water liquid and water vapor, they are in equilibrium. This is the sign of equilibrium. Half arrow in forward direction and half arrow in backward direction. Now come to the characteristics of equilibrium. Equilibrium can be achieved in closed system only, where the product and reactants both are present in the reaction vessel. Equilibrium is achieved when the rate of forward and reverse reaction becomes equal. At equilibrium, there is no further change in the concentration of reactant and product. That means they have attained a constant value. When system is in equilibrium, it doesn't give 100% yield of product. Now come to the law of mass action. It states that the rate of chemical reaction at each instant is proportional to the concentration of product of all the reactants. Or mathematically you can write rate is directly proportional to the concentration of reactant A multiplied by the concentration of reactant B and so on. Here concentration is expressed in molarity or in moles per liter. Now apply the law of mass action to the given reaction, where A reacts with B and gives C. On applying law of mass action, you can write the rate of reaction is directly proportional to the concentration of A multiplied by concentration of B. When you remove this proportionality sign, you will get a constant. So here you will get rate is equal to K multiplied by concentration of A multiplied by concentration of B. Here K is the rate constant. Now apply the law of mass action to this equation, where small a moles of capital A reacts with small b moles of capital B and gives C. Here the rate will be directly proportional to the concentration of A raised to the power A, concentration of B raised to the power B. Now remove this proportionality sign, so you will get a constant. Concentration is expressed in square bracket. It is also known as active mass. Concentration is expressed in molarity, or the unit is mole per liter. Here you need to remember that the concentration of pure liquid is considered as 1 and the concentration of pure solid is also considered as 1. Now come to the equilibrium constant. Here small a moles of A react with small b moles of B. They are in equilibrium with C moles of C and D moles of D. Now apply the law of mass action for the forward reaction. For forward reaction, small a moles of A and small b moles of B are the reactants. So you will get rate of forward reaction is directly proportional to the concentration of A raised to the power A multiplied by concentration of B raised to the power B. Now remove the proportionality sign. So you will get rate of forward reaction is equal to Kf, where Kf is the rate constant, multiplied by A raised to the power A and B raised to the power B. Now apply the law of mass action for the reverse reaction. For the reverse reaction, C moles of C and D moles of D are the reactants. So rate of backward reaction will be directly proportional to the concentration of C raised to the power C multiplied by D raised to the power D. Now remove the proportionality sign, so you will get rate of backward reaction will be equal to rate constant for backward reaction multiplied by C raised to C and D raised to D. So here we have got rate for forward reaction and here is the rate of backward reaction. At equilibrium, rate of forward reaction becomes equal to rate of backward reaction. So we can equate both the equation. So here you will get rate constant for forward reaction multiplied by A raised to A, B raised to B is equal to rate constant for backward reaction multiplied by C raised to C and D raised to D. Now transfer the constant terms on the one side. So you will get Kf over Kb is equal to C raised to C, D raised to D over A raised to A multiplied by B raised to B. Ratio of Kf and Kb is known as Kc, which is the equilibrium constant. Here K is the constant, here C stands for concentration. Now come to the equilibrium constant. It depends on the balanced chemical equation. Its unit also depends on the stoichiometric constants of the balanced chemical equation. It is a constant for a set of pressure, temperature, volume and concentration. Now let's see how Kc changes when reaction is reversed. So here it is the original reaction where small a moles of A reacts with small b moles of B and they are in equilibrium with C moles of C and D moles of D. Now let's write the equilibrium constant for this given equation. So you will get Kc will be equal to C raised to C, D raised to D over A raised to A, B raised to B. Now reverse this equation. So here product becomes reactant and reactant becomes product. So you will get the equation C moles of C reacts with D moles of D and they are in equilibrium with A moles of A and B moles of B. Now write the equilibrium constant for this reaction. So here you will get K dash C is equal to A raised to A, B raised to B over C raised to C and D raised to D. Now when you compare Kc with Kc dash, so you can see here Kc dash is just inverse of Kc. Means when you reverse the reaction, new equilibrium constant will be the inverse of old equilibrium constant. Now let's see how Kc changes when the reaction is multiplied by some factor n. Here the reaction is nitrogen reacts with 3 moles of hydrogen and they are in equilibrium with 2 moles of ammonia. So when you write Kc, you will get concentration of ammonia raised to the power 2 as there are 2 moles of ammonia divided by concentration of nitrogen multiplied by concentration of hydrogen raised to the power 3. as there are 3 moles of hydrogen. For example, when we multiply this equation by 2, so you will get 2N2 plus 6H2 in equilibrium with 4NH3. Now write Kc for this new reaction. So you will get Kc dash will be equal to concentration of ammonia raised to the power 4, as there are 4 moles of ammonia, divided by concentration of N2 raised to the power 2, multiplied by concentration of hydrogen raised to the power 6. Now compare Kc with Kc dash. Here you can see Kc dash is the square of Kc. When you take the square of Kc, you will get Kc dash. So you will get the general formula. Kc dash will be equal to Kc raised to the power n when you multiply the reaction by some factor n. As here we have multiplied the original equation by 2, so new Kc dash will be the square of old Kc. Now see what will happen to Kc when the reaction is divided by some factor n. Here I have taken the example of H2 reacts with I2 and it is in equilibrium with 2Hi. Now write the Kc for this equation. So you will get Kc will be equal to concentration of Hi raised to the power 2 divided by concentration of H2 multiplied by concentration of I2. Now if we divide this equation by 2, so you will get the new equation half H2 plus half I2 in equilibrium with Hi. Now write the Kc dash for this equation. So here you will get concentration of Hi divided by concentration of H2 raised to the power half multiplied by concentration of I2 raised to the power half. So here you can write it as concentration of Hi divided by root of concentration of H2 multiplied by root of concentration of I2. Now compare Kc dash with Kc. So here you can see if we take the root of this Kc, you will get Kc dash. Or you can get the general formula Kc dash will be equal to nth root of Kc.